Hi, I'm Tulin Bragg. Myself and Anthony Carolla were marking some of the 2021 advanced mathematics questions in this year's HSC. The first question we marked was question 15. It was the evaluation of a square root of 2x plus 4. The solution required students to understand the square root becomes a half, and they needed to do the appropriate substitutions after the integration. So the syllabus for this, the content was establishing the antiderivative using the formulas given, and also to use the substitution of the upper and lower limits. What students should do, therefore, is express the integrand using index notation. They could also have the option of using the reference sheet, which is on to find that standard integral. They need to show the substitution into their primitive. They needed to then use a calculator to find a simplified numerical solution. And they need to then differentiate they could have also differentiated the antiderivative to check that it actually matched the given integrand. What we did find is that better responses showed that the calculus notation was done correctly. They were able to express the integrand in terms of a fractional power. They were able to substitute limits into primitives correctly. And students were evaluating numerical expressions involving a fractional index, so that whether they used a calculator or whether they knew to do it without a calculator, that was also acceptable. What we found was the areas for students to improve included appropriately manipulating the numerator and denominator of the integral. So a lot of the students, instead of putting the 2 over 3 times 2 in the front, so bringing the 3 over 2, they were unable to do that. They were also some of them struggled with distinguishing between the chain rule and the reverse chain rule. They were having difficulties with integrating functions involving roots and fractional indices. So they were, instead of adding a half, they subtracted a half, for example. Simplifying fractions involving a fractional denominator. So dealing with the denominator, leaving it as a fraction was also, and not simplifying that, created problems. Explicitly showing substitutions into the antiderivative using brackets. So a lot of students didn't use brackets, and it just led to a lot of confusion in actually working out what the answer was. So if they actually showed the working, and it became a very simple exercise after that. They needed to evaluate the resulting antiderivative to give the fully simplified numerical solution. So they needed to work all the way out what 4 to the power of 3 on 2 was, rather than leaving it like that. And they need to, so the idea here is to develop a habit of checking the antiderivative of integrals by differentiating. So they could have made sure that they were able to, or be more assured that it is the correct derivative when they were doing the reverse chain rule as well. So the next question was 16. We're looking at, the question just simply says, for what values is this function increasing? So we're looking for the knowledge that the actual derivative is required here, that they know that the function is increasing when that derivative is positive, and then being able to solve a quadratic inequality. So we are looking for, specifically in the syllabus where it says f dash x is positive when the function is increasing. So students should use calculus to determine the first derivative, and then state that that first derivative is increasing, the function is increasing when the first derivative is positive. They solve the resulting quadratic inequation by graphing or using a sign diagram. Either one would work. Setting out the working very clearly and logically was important here. And then finally answering the question, which was stating what the domain is. In better responses, students found actually stated the condition for an increasing function. They found the first derivative. They factorised the derivative to find the x-intercepts. They solved the quadratic inequation by graphing a concave down parabola. Some students were able to resolve the negative leading term by multiplying every term by -1 and also changing the sign of the inequality, which worked quite well as well. They were able to solve the quadratic inequation by testing critical points on the number line, and then found the domain answering using set notation or interval notation. What we found here was the students needed to understand that sketching the function by finding minimum and maximum points was not necessary, but it is obviously a way of doing it, albeit a long one. In question 16, the areas for students to improve is looking at differentiating cubic functions. Even though it's quite a simple function, that a bit more practice in that would have helped. Recognizing the first derivative corresponds to the gradient of a function. A lot of students were confused a little bit about that. Associating an increasing function with the fact that the derivative is positive. Solving quadratic equations and inequations with a negative leading term. And more importantly here, what I think was knowing the difference of the sign of f of x, f dashed x and f double dashed x. So we're looking at each of those separately and understanding what each of those separately means, and expressing the domain using interval notation or inequality signs. So that's actually answering the question at the very end. So because the paper didn't actually have a question where it says, you know, draw this function and show the minimum maximum points, we had a fair few students who actually thought that this might have been it. So while they answered the question, it was done in a very long way by finding all of those turning points, which really lost the essence of the question, which was just for what values of that is that function increasing. Question 21. So this is the transformations question, where a given function was given, a graph of a function was given, and students needed to sketch y equals 4 times f of 2x. The question asks to show the x-intercepts and the coordinates of the turning points. So in the solution, we're looking for a horizontal dilation by a scale factor of 1/2 and a vertical dilation by a scale factor of 4. So the 0 zeros is maintained, the 4 minus 8 becomes the 2 and then the minus 32, and the 6 0 becomes 3 0. And so we're looking for a graph showing the minimum at 2 minus 32 and the x-intercepts 0 and 3 and the maximum maintained at 0 0. So we're looking at dilations here in the syllabus. It's k f of x, y equals k times f of x and y equals f of ax. Students should identify that a horizontal and vertical dilation is required. They would deduce that y equals f times f of 2x is a dilation horizontally with a scale factor of 1/2, and y equals 4 times f of x dilates the function vertically with a scale factor of 4. And then, of course, we need to actually sketch the cubic graph showing the transformed x-intercepts and turning points. In better responses, students understood the geometrical significance of the 4 and the 2 in the new function. They were able to calculate the horizontal and vertical dilations. They appreciated that the origin is maintained as a maximum turning point after dilations. They were able to compress the cubic curve by a factor half to transform the x value of 6 to an x value of 3. They were able to stretch the cubic curve by a factor of 4 to transform the y value from -8 to -32. Some students drew successive graphs representing progressive transformations. So one to compensate for the horizontal and the other to compensate for the vertical. They used appropriate scale to show x and y values, and they were able to draw a continuous cubic curve where they labelled all their turning points on the graph. Question 21, the areas for students to improve include separating the transformation into horizontal and vertical components rather than attempting both simultaneously. They need to distinguish between a dilation and a translation in the horizontal and vertical directions. They would need to understand horizontal dilations affect the abscissa, which is the x values only, and the vertical dilations affect the ordinate, which are the y values only. Systematically focusing on the critical points provided in a graph. So we're just looking at the turning points and intercepts rather than any other point. We need to clearly label critical points on a graph, which is especially drawn not to scale. So that was important. We need to see where those values, the minimum is. Actually, if it's not to scale, it needs to be highlighted or explained what it is. If we develop a systematic method for applying transformations to sketch functions, that would be helpful. And a great way of practicing with these is using Desmos or GeoGebra, and it is a really good way of emphasising what the K and the A, how they affect the final function, the graph of that function. Question 22 is a long worded question. So students obviously needed to understand what the question is actually asking, what it's explaining, and they are all important information here that needs to be read. So what we need to do for part A was using the table, we wanted to find the probability that a value from a random variable that is normally distributed with a mean of 0 and a standard deviation 1 actually lies between 0.1 and 0.5, noting that it's only worth 1 mark. So the solution is to find the difference between those z-scores and the probabilities given by those z-scores. And it's using statistical tables to determine probabilities in the syllabus. So what students should do is read the whole question carefully to understand what is represented by the data in the given table. We need to use the given information to calculate the desired probability, understand the relationship between the probability of 2 z-scores and the position of the z-scores on the bell curve. And we need to subtract the probability value for a z-score of 0.1 from the probability value of a z-score of 0.5 using the table provided. In better responses, students were able to understand that the shaded area represents the probability that a random variable lies between the mean and the z-score. Now that's actually stated in the question. So, and we've probably, if students had read that maybe twice, it would have helped. And that's what I would recommend with those long worded questions, that students actually read it not just once, but at least twice before they attempt. Understand how probabilities interact with z-scores. They would identify the correct probability values to use from the table and use the given graph depicting the normal distribution to find the difference between the two probabilities. Areas for students to improve include connecting the probability between two z-scores and the position of the z-score on the bell curve. Understanding that subtraction is required to find the probability between two z-scores. Practicing questions with z-scores and the normal distribution to familiarise with the language used in probability questions. Appreciating worded questions provide necessary information. And reading heavily worded questions which set up simple scenarios involving course content. And of course, understanding that questions with 1 mark require a simple step. So this is obviously a new component of the syllabus, and it does, I think it is very helpful if we do practice a lot of practice with students questions that are not so straightforward, that actually exactly like this one, where you read information and you use that information to answer the question, rather than using your own notion of say empirical scores or anything else. So we really do want students to read the question, absorb the information given in the question, and then use that information to answer the question. The second part of this question requires birth weights are normally distributed. So what we need to do here in the second part of this question for 3 marks is we're looking for, first of all, the question asks us to find a z-score. So it's very specific. By first calculating a z-score, find how many babies out of 1,000 born are expected to have a birth weight greater than 3,528 grams. So we are finding the z-score first, and then we're looking for that to be greater than that z-score, which becomes 0.4, and we're using the distribution to find out the exact probability, which we're then multiplying by 1,000 since there's 1,000 babies. There's the syllabus content here. The first part is obviously just the z-score, which is also given in the reference sheet. Then we're also looking at recognising how to use the probability density function of the normal distribution with the mean and the standard deviation. So what students should do is use the reference sheet to find the z-score formula and then substitute values correctly. So they need to substitute into the formula that they see or what they've learned, checking that they substitute the mean and the standard deviation correctly. Then they use the z-score to find the corresponding probability, again from the table that's given, and then understand the connection between the results provided in the table and the shaded area under the normal distribution bell curve. If they draw the bell curve to understand the value of their probability in terms of the position of the mean, that's also very helpful. And then, of course, finally, the question does ask to find how many babies, so we're multiplying that probability by 1,000. So in better responses, students did identify each of those variables in the, to substitute into the z-score formula. They were able to generate a probability from a z-score given a table of the probabilities. They were able to recognise that the right side of the normal distribution represents the required probability. So they were then required to exclude half the scores below the mean. And then finally, they multiplied their probability by 1,000. Now, areas for students to improve include calculating a z-score. So we had students that were not quite sure which one was the mean, which one was the standard deviation. So that was a bit confusing. We found that students need to equate a normal distribution to a continuous probability distribution that is symmetrical on both sides of the mean. They need to understand the symmetrical nature of the distribution. Connecting z-scores with probability of scores being above or below that z-score was important. understanding what is represented by the empirical rule and the area under a normal distribution curve, avoiding the empirical rule represented with a table of probabilities. So we don't want students using the 68 and 95 when we've already got Z-score table there with probabilities. And then linking probability to the area under a normal distribution bell curve, and reading the question again to check if it has actually been answered. So a lot of students found the correct probability, but not the number of babies. So the last question here was a great question, which really mixed a few topics together very well. So we're looking at, it is a show that question, and we're looking at quite a few topics and quite complicated algebra in this question. So a discrete random variable has probability distribution as shown in the table, where n is a finite positive integer, and then we have to show the expected value is equal to n times 2r minus 1. Now, the solution is we use the sum of the probabilities. We know that the sum of the probabilities equals to 1. And then we see that it becomes a GP with the first term r and the common ratio also r with n terms. So because it's a GP, we're using the GP formula and making it equal to 1 and cross multiplying, and then we work out what r to the n plus 1 is. So make r to the n plus 1 the subject. Now we know the expected value is equal to the terms top and bottom multiplied together and added. So when we do that, we get r to the n plus 1 n times, and we are then replacing the r to the n plus 1 with what we found earlier with 2r minus 1, and that's how we proved it. Now here we are looking at using discrete random variables and associated probabilities to solve practical problems. We're using the sum of a GP, and we're using complex algebraic expressions and simplification of algebraic expressions. So students should use the reference sheet to write down the formula for the expected value. They need to fully simplify the series. They need to equate the expression for the sum of the probabilities equal to 1. They need to express the sum of the probabilities as a geometric sequence and manipulate the algebraic fractions carefully and make the connection between the expression for the sum of the probabilities and the expected value to show the desired result. In better responses, students used the expected value n times p to generate the series. They recognized the pattern to simplify the expected value to n r to the n plus 1. They equated the algebraic sum of the probabilities to 1. They used the sum of the geometric sequence to show that r to the n plus 1 equals 2r minus 1, and then they rearranged the algebraic expression and were able to link both equations and connect to show the required result. Areas for students to improve include familiarising with the reference sheet to write down the geometric sequence formula. Now we did, that was obviously given, but the fact that it equals to 1 was also required for the GP. Understanding the difference between the expected value with that formula and the arithmetic mean. Understanding that the sum of the probabilities equals to 1. The important thing here was distinguishing between an arithmetic and geometric series. Some students were confused. They assumed that it was arithmetic. And then distinguishing between a geometric series with and without a limiting sum. So some students thought that it was a limiting sum, so that there was a different formula used. What we found was students who reversed the geometric series to simplify the substitutions in the formula were better off because it started with r rather than then r plus r squared plus r cubed, etc., rather than r to the n and going down that way. If they fully simplified algebraic expressions by using index laws, that was required, and it helped them do if they did that. Appreciate that the question is asking for show that. I mean, we've seen this many times before where students are not quite sure about how to actually get the final answer. And it's important that they show all the steps for that, because it needs to link, everything needs to make sense. So I think that's it. That was it.